Hi and welcome everyone. In this lecture, I want to go over linear transformation, give you an introduction of linear transformations, and then the next lectures we'll see how they're used. So first definition, a linear transformation, that's how you write it, T from Rn to Rm. So this is the domain and that's the codomain. So is a function that's satisfied for two vectors u and v in Rn and a scalar R, these two properties. The additivity property T of u plus v should be equal to T of u plus T of v. This is just like vector addition when we talked about in vector spaces, kind of like that. And the homogeneity property T of k u should be equal to k times T of u, and that's the scalar multiplication. Now there's a special case where the transformation goes from Rn to Rn. The domain is the same space as the codomain. We call that type of transformation a linear operator. So please remember that word. Now let's do an example. You have a transformation from R2 to R3. And that's how it's written. T of xy is going to give you the first component as 2x minus 3y, the second component as x plus 2y, and the third component is negative x plus y. If we try a vector here, negative 5, 7 as components, you just substitute for x, y, and the final answer, you substitute and do the arithmetic, you get negative 31, 9, and 12. We are going to come back to this. First, let's check to see if that's a linear transformation. So if you want to prove that a transformation is linear, just go over the two properties. So what, and to start that, just pick a vector T of x1, y1, and just write the transformation. Another one, T of x2, y2, write transformation for x2, y2. And always we need a scalar. Here I called it k, which is a real number. So the first one, the additivity property, this needs to be satisfied. So let's see if we do T of x1 plus y1, wherever you see x, you just substitute by x1 plus x2. And wherever you see y, substitute that by y1 plus y2. So if you do that, you get those three components. So it's 2 times x1 plus x2 negative minus 3 times y1 plus y2. The second component is x1 plus x2 plus 2 y1 plus y2. And the third component is negative minus x plus y plus y, x1 plus x2 and plus y1 plus y2. So this was our x, y, x, y, x, and y. Basically, you substitute x by x plus 1 and y, x1 plus x2 and y by y1 plus y2. If you get rid of the parentheses, you get that expression, but what you can do is separate them. Just write that as the first one, 2x1 minus 3y1, so these two. And then the first component of the second vector, just write that as 2x2 minus 3y2. And the third one, so you can separate the second one again, it was x1 plus 2y1, and the third one is negative x1 plus y1, and plus negative x2 plus y2. When you do that, you notice that this is just T of x1, y1, and that one is T of x2, y2. So we do get T of u plus v equals to T of u plus T of v. So addition is satisfied. Scalar multiplication, we want to see if that's satisfied. So do the same thing. T of k times xy is k times that 2x minus 3y, x plus 2y negative x plus y. And if you can distribute the k to all of them, so you get that. And then if I kind of separate this, here we have kx, ky, kx, ky, kx, ky, and that's just t of kx, ky. So t of kxy is the same thing as t of kx, ky. So scalar multiplication or the homogeneity property is also satisfied. So you can say this is a linear transformation. Now, what's special about linear transformation? I can come up with this matrix. And this is the x column, and that's the y column. The way you write it, for x's, we have 2x, x, and negative 1. So you write 2, 1, negative 1. For y, we have y values, we have negative 3y, 2y, and y. So basically, it's negative 3, 2, and 1. And if you multiply that by a 2 by 1 vector, then let's see what happens. If I pick negative 5 and 7 and I perform the matrix multiplication, you get negative 31, 9, and 12. So negative, which is a vector, that's a 3 by 1 vector. So that's what we get. And if you notice, when we perform the transformation and we started for negative 5 and 7, we did get the same number. So what's the conclusion? It's this theorem. A function t from Rn to Rm is a linear transformation if and only if we can find an m by n matrix, again, m by n matrix, so that the action t can be performed by matrix multiplication. This is a notation. You say the transformation is the matrix A times X. So again, this is a transformation from Rn to Rm. Your matrix has to be an m by n matrix, m by n, m rows and n columns. This is a vector matrix, is m by 1. So if you do transformation, you get an m by 1 matrix. Little note here, if T, the transformation goes from Rn to Rn, then you are going to be dealing with a square matrix, and as I called in the beginning of the lecture, that's called the linear operator. I did put a note here for you too. Sometimes instead of A, you're going to see this notation for the matrix. We also put it inside brackets, but that's the same thing as matrix A. I think that's it for this lecture. In the next lecture, we are gonna use matrices to see how transformations work for addition, multiplication, and inverse matrices. Thank you for watching, and I'll see you soon in my next video.